Okay, in this video we're going to talk about the leading and lagging strands. So remember, we had this problem where we have this rule, two rules. One is we can only lengthen DNA using DNA polymerase if we have an RNA primer for the DNA polymerase to attach to. So we first have to have a complementary RNA primer after we separate those two separate template strands. And the second rule is the lengthening of the DNA must proceed in a 5' to 3' direction. That's because it's the 5' end of the incoming nucleotide that contains the phosphates that will be cleaved off by DNA polymerase and provide the energy to attach this 5' end to the free 3' end of the strand that already exists. So when we grow a DNA strand, we are always adding to the 3' end. So that incoming nuke always orients with its 5' end to attach to that 3' end. And so as we lengthen DNA, it's always growing 5' toward the 3' end. And this 3' end is the end that we can attach new molecules to. We wouldn't be able to do it in the other direction because we need this incoming nuke to have the energy in those phosphates, and those phosphates are going to be in the 5th carbon. Okay, but the problem is at the replication fork, because the parent strand, or really any DNA strand, is anti-parallel, that means that when we divide them, or when we separate the template strands, complementary DNA, when we separate it, one of the strands is going to have a free 3' end, and the other strand is going to have a free 5' end. Because remember, these strands are anti-parallel. One strand runs 5' to 3', and the other strand runs 5', or I'm saying them the same way, but it runs I'm drawing it, so it runs in the opposite direction. So for one of the strands, which is called the leading strand, this is fine, no big deal. We separate the DNA out, and as we do so, we've got this free end here. We're going to make first a primer. So here's our little yellow primer. It's going to be complementary here. And if this end is 3', this end from our primer is going to be 5', which means that right here is its free 3' end. And that's what we want to attach to. So here comes our 5' end with all those phosphates, kind of trying to draw it, and it would be able to attach right there. And so as we grow in this direction, it's no problem because we can just bring in that 5' end and bind, and then we can just keep going and keep lengthening as that replication fork. So remember, we have helicase is coming along, breaking the hydrogen bonds, separating these, and this replication fork is going to continue separating the DNA as you push it forward. And this leading strand is going to have no problem with that. As you separate the two strands, it's just going to keep adding and lengthening this new strand of DNA. So no big deal for the leading strand. It's synthesized as one long continuous molecule because it's adding in the same direction as the replication fork is moving. Now the other strand is going to have a problem because the other strand, it's anti-parallel, so its 5' end is over here, and in order to use it as a template, we're going to put in, let's say we put in the primer right here. So this is the 5' end of the primer, and this is the 3' end of the primer. So here comes a little new nuke. Here's its 5' and 3' end. This 5' end is going to be able to lock in here, and then we'll be able to add another one. 3' is going to be able to lock in here. But we're going in the opposite direction as the replication fork. So as the replication fork continues to move up, well, we started here and went this way. So how are we going to synthesize this new DNA that we just opened up? What we're going to have then, these are going to be called, this is called the lagging strand, and it's going to form a series of small fragments called Ogasaki fragments. And that's because it's lengthening in the opposite direction as the fork is moving. I think I can show you that here in this next picture. So here was our first strand. We put in a little primer, and we grew the DNA this direction. But then the replication fork kept opening up and we had all this exposed DNA. So we put in a new primer here and started going this way. But then the replication fork kept pushing open and we'd have to then put in another primer here and go this way. And so each of these little fragments is called an Ogasaki fragment. And these individual Ogasaki fragments are going to have to be ligated together. So what's going to happen next is we're actually going to remove the primer. So the RNA primer gets removed later. And then you're left with this gap. And what will fill in that gap is a enzyme called DNA ligase. So DNA ligase is going to be the player that's going to ligate the Ogasaki fragments together. So DNA ligase, this is our 6th protein that was in that original list for replicating DNA. DNA ligase is only used on the lagging strand, and it's used to connect or to ligate the Ogasaki fragments together. And so as the replication fork continues to push this way, separating more and more DNA, you're going to put in a new primer and make more DNA grow this way, and then we're going to have to connect these Ogasaki fragments together again with DNA ligase as well. And as we continue to push that replication fork, we'll see this will happen again and then again. And so in the lagging strand, we're going to have these Ogasaki fragments and we're going to have the need for DNA ligase to ligate them together. The leading strand doesn't have that problem because it just keeps adding in the same direction that replication fork is being separated. Okay, so this gives us a pretty complete view of how DNA is replicated. You have to separate the strands. That's done by helicase. You have to prevent them from religating. That's done by the single strand binding proteins. That prevents them from reconnecting, as you have these free nukes and these free nukes so that they don't just rejoin the single-stranded binding proteins. I say they look like shrimps, but they kind of cover those free hydrogen bonds. You have topoisomerase was the one that was as you separate so that you don't get kind of these super twists in the DNA ahead of the replication fork. And then we have primase, putting in these little RNA primers that DNA polymerase needs, because DNA polymerase can only wrap itself around DNA and a little piece of RNA to get started doing its job. What DNA polymerase does is it connects those sugar phosphate backbones of the incoming nucleotides. So it polymerizes the growing strand of DNA that we're making. And then finally, the last one that we need is DNA ligase, and it's only needed because the two strands, one's called a leading strand, it does not need ligase, but the lagging strand does need the ligase because of how it's having to build the DNA. It has to always grow one piece, which is an Ogasaki fragment, and then it has to come back here and grow another piece, and then these two separate pieces have to be ligated together. Okay, so that gives us a pretty complete view of how DNA is replicated. A couple topics to talk about then. One is proofreading. For one, this process has high fidelity. That means it makes very few mistakes. The reason it makes very few mistakes is largely because of those hydrogen bonds. They're going to be more stable between A and T than they would between C and G. If you get a mismatch where, for example, a G has tried to form a hydrogen bond with an A, it's going to kind of make a weird bump in the two strands of DNA. And this will be corrected because they do not. The DNA is not correct with that. So those hydrogen bonds are more stable when they are correctly matched, and if they're incorrectly matched, DNA polymerase will actually remove those mismatches. It will not ligate them, or it'll actually break those ligations if it does, so that we don't have any mismatches. It says DNA polymerase does not form those covalent bonds at places where there are mismatches, and it will actually remove those mismatches, so actually take them off. So this is a very high fidelity process. Very few mistakes are made, so that when you replicate DNA, you replicate it in its entirety. Now, the very last topic to talk about is in how I describe things, there is a problem. And the problem is DNA polymerase will never be able to copy what's called a 3' overhang, because it can only work in the 5' to 3' direction, and it needs a primer. So in order to make this DNA, there was a primer right here, an RNA primer right here that the polymerase attached to, and it moved along. But the problem is you remove this, you remove this primer, and you now have no way of putting in this DNA piece here because there's nothing for DNA polymerase to attach to. And so we cannot add nucleotides back in to this little piece here. We can't get the nucleotides attached. And this would be a problem as you continue to replicate DNA. If you always have this overhang and this little piece that you can't transcribe, over time your DNA is going to get shorter and shorter because you're going to have more and more pieces that aren't being replicated. So because we can't make the complementary pieces with RNA or DNA polymerase here, we have this 3' overhang and we have this problem. And so to overcome this problem, we have what are called telomeres. All chromosomes or all DNA sequences have a telomere at the end. And what a telomere is it's a nucleotide sequence repeated several hundred times. And so, for example, this nucleotide repeat sequence could be something like GGGTA. And we're just going to add that over and over again at the ends of all pieces of DNA to lengthen the DNA. And so that if we do shorten it a little bit, we're just losing these little telomere repeats that nobody really cares about because they're not coding. These little repeat sequences do not correspond to a gene, and they do not give you the directions to make a protein. That's what a gene would be. A gene would be a sequence of DNA that gives you the instructions to make a protein. This little telomeric sequence of DNA is not going to give you the directions to make a protein. It's just going to kind of be this little sequence of DNA, kind of like junk DNA, but it's not junk. It is a telomere. It is going to be these repeated ends. And in order to make the telomeric ends, we have an enzyme called telomerase. It's going to attach these repeated units of DNA to the ends of all eukaryotic chromosomes. And so what telomerase does, what this enzyme does, the telomerase enzyme is going to contain some RNA in its, so it's a protein, but it includes some RNA. And I think, okay, so in this picture, I'm kind of jumped ahead, but this picture, the big brown blob, shows telomerase. So telomerase is a protein that's signified by the big brown blob shown here. And then telomerase, in addition to just being a protein, it includes an RNA moiety. So part of this molecular entity, which is telomerase, includes this RNA piece. And the RNA piece is a repeated nucleotide sequence. And you can see this repeated nucleotide sequence. It's AAU, because if you remember way back, RNA has U instead of T, and the U is complementary to the A then. But so this telomeric sequence is AAU, CCC, AAU. And so the the telomerase, this big enzyme, is going to include this RNA sequence because it's going to use this RNA sequence in order to grow the 3' end of the DNA. So it grows this 3' overhang. So the end of the DNA, the 3' end of the DNA, will have this sequence that, for example, looks like TTA, GGG, TTA. So that's at the 3' end of the DNA sequence. And telomerase is going to make that sequence repeat over and over again, maybe 100 more times. And so what happens, this great big brown telomerase molecule binds because it includes this complementary RNA sequence. And this complementary RNA sequence will hydrogen bond with the complementary bases in the 3' overhang of the DNA. So it binds because if you read, these guys are complementary. AAU is complementary to TTA. And then the CCC is complementary, if I kind of go back up here, to the GGG. And then AAU is TTA. And so this RNA piece would bind to the 3' overhang. And when it does, it binds in such a way that it leaves these guys kind of exposed so that a new nucleotide, if it's got this little C exposed, a new nucleotide will bring in the G and kind of hang out here. Here's the G, and then another G, and then another. And then what the telomerase does is it attaches these nukes. So we're bringing in these nukes. So here comes in a nuke. It's got its 5' because that 5''s got all the phosphates. So that 5' comes in and binds to the free 3' end. And this 5' end will have that nuke. Let's say it's a G in this case. And then that'll leave a new 3' end. But then the next complementary base will come in and attach to that 3' end. So we can grow out the 3' end and lengthen it. And we do this with telomerase. So if I just jump back to see if I hit all these notes. So telomerase is a big enzyme composed of both protein and RNA. That RNA is going to be complementary to the 3' end of the DNA so that telomerase can bind to the 3' overhang. And then the rest of this RNA sequence will serve as a template, allowing telomerase to synthesize this nucleotide repeat sequence. And then telomerase jumps ahead and does it again. This will eventually provide enough upstream sequence so that we can have an RNA primer form using DNA primase, and then DNA polymerase can bind to it and actually copy this 3' overhang so that it's no longer a 3' overhang. Let's finish these pictures and see how that happens. So going back, we kind of messed with this picture already. This next picture shows how telomerase will then move down and do it again. So because telomerase has this RNA sequence that's somewhat complementary to the 3' overhangs, it provides this template that brings in new nukes and adds lengthening this 3' end. And then telomerase will release and bind further down. So this whole thing will move down so that now maybe these AAs shift down, so now they're here. So now here's these AAs attached, hydrogen bonded here, and we can bring in new nukes, and then it'll shift over and it'll do it again over and over until this 3' overhang has lengthened enough. So we're really drawing out this 3' overhang so that it's really long. Because the problem was, with it only being a very short 3' overhang, there's not enough room to add the RNA primer for polymerase to bind to the RNA primer and make that complementary sequence, because then you remove that primer and you have a 3' overhang again. By lengthening it out like this, we then have this longer 3' overhang, and then we can put in that RNA primer, and then polymerase can bind to the whole thing, and add the DNA back, ultimately, we're still going to get rid of this primer, but the idea is we've grown this whole thing so much that when you eventually get rid of this primer, and yeah, no matter what, there's still going to be a 3' overhang. But if we add this, and telomerase does this hundreds of times, so we're going to have this repeat just lengthening the heck out of our 3' overhang so that we can then put in a primer, and then we can make a complementary. And if you note, I mean, what we're putting in that's complementary is this telomeric sequence. So the ends of the DNA are kind of boring because they're these repeated telomeric sequences. But that prevents, even though you're always going to have this 3' overhang that cannot have complementary DNA attached to it, it won't matter. Because this is not going to be a coding sequence. This is not going to be a gene. None of this is going to be a gene, in fact. It's all just going to be this boring telomeric sequence that nobody really cares about. But if you didn't have it, the fact that this little piece of DNA, or really it's RNA here, the fact that we can't copy this little piece of DNA with a complementary strand would have been a problem had this been a gene or something really important to your genetic material. We would, without the telomeres, our DNA would be shorter every time because we would always have this 3' overhang that we can't make the complementary DNA to because of this whole needing the RNA primer and this RNA primer eventually being removed. And when you remove it, you got this 3' overhang that doesn't have anything complementary to it. And without telomerase, the DNA would get shorter and shorter and shorter. So we have to have the ends of our DNA lengthened with telomerase. And so this gives us all of the information we need. I did, however, skip the password for this week, even though I left it as a hint for myself to remind myself to mention the password. Our password this week is the word polymerase, and I did check, it is 10 characters, so the whole thing should fit and everything should work fine. So that password is POLYMERASE, which is polymerase, which in my opinion is kind of the main star when you think about DNA replication.